January 15, 1944. Wright Field, Ohio. Snow covered the runways, and the air smelled of fuel, oil, and quiet fear. Inside a massive hangar, under harsh yellow lights, stood the most expensive weapon America had ever built. The Boeing B-29's Superfortress. To the public, it was a symbol of unstoppable power. To the engineers standing beneath its wings, it was a nightmare waiting to happen. 4 engines hung from the wings, each one capable of producing more power than any aircraft engine before it. But those engines were also killing crews. Not in combat. Not over enemy territory. They were exploding during training flights over the United States. Entire aircraft were being lost before ever seeing Japan. Fires erupted without warning. Wings tore away. Crews had seconds to react, if they had time at all. The B-29 was supposed to win the war in the Pacific. Instead, it threatened to become the most catastrophic engineering failure in aviation history. And the terrifying truth was this: the enemy was not Japan. The enemy was heat. Physics. And an engine pushed beyond anything humans had ever controlled before. At the heart of the problem was the Wright R-3350 duplex cyclone engine. On paper, it was a masterpiece. 18 cylinders arranged in 2 rows. Air-cooled. Over 2,200 horsepower. It was designed to lift the B-29 higher, farther, and faster than any bomber before it. But reality was cruel. The rear row of cylinders received almost no cooling air. Temperatures climbed beyond safe limits. Oil leaked under pressure, sprayed onto glowing exhaust components, and ignited instantly. Engine fires became so common that crews joked darkly about them, even as friends died. Pilots reported flames shooting backward over the wing. Fire suppression systems failed. Feathering the propeller sometimes made the fire worse. Investigations followed every crash, and every report told the same story. The engine was operating at the absolute edge of materials science. Metal warped. Bearings failed. Valves burned. And yet, abandoning the engine was impossible. There was no replacement. The B-29 was built around it. If the engine failed, the bomber failed. And if the bomber failed, the Pacific War stalled. American leadership faced a brutal choice. Delay the program and give Japan time to recover, or push forward and accept losses. They chose to push. But engineers refused to accept that this was the best that could be done. The first breakthrough came not from power or strength, but from understanding airflow. Engineers discovered that cooling air inside the engine cowling was behaving nothing like the calculations predicted. Instead of flowing smoothly over the cylinders, it stagnated. Heat became trapped exactly where it was most dangerous. Using smoke visualization and early wind tunnel tests, they saw invisible walls of dead air behind the front cylinders. The solution was not more air, but controlled air. Engineers redesigned internal baffles, forcing airflow through precise paths at specific speeds. Tiny changes made massive differences. A curved deflector here. A sealed gap there. Cylinder head temperatures dropped dramatically. Engines survived longer. Fires became less frequent. For the first time, it felt like the engine might be tamed. But cooling alone would not save it. Oil remained the silent killer. The R-3350 used enormous quantities of oil, pumped at high pressure through a complex internal network. Under extreme heat, seals failed. Oil mist filled the engine nacelle. When it touched exhaust parts glowing red-hot, the result was instant fire. Engineers attacked the problem from every angle. New seal materials were developed. Oil-scavenged systems were redesigned to prevent pooling. Fire-resistant coatings were applied to vulnerable surfaces. Automatic fire suppression systems were improved to react faster and flood the engine compartment within seconds. But every fix added weight. And weight demanded more power. And more power meant more heat. The engine was trapped in a vicious cycle. To escape it, engineers had to do something that seemed impossible. Improve reliability without increasing weight. Reduce failure without adding complexity. It required not brute force, but intelligence. That intelligence came from information. Early B-29s gave pilots very little warning before an engine failed. By the time a needle moved into the red, it was already too late. Engineers realized they didn't just need stronger engines. They needed engines that could speak. New sensors were added to monitor temperatures, pressures, and vibration in real time. Crews were trained to recognize subtle changes before disaster struck. A slight rise in oil temperature. A small drop in pressure. These became signals, not surprises. Pilots learned to reduce power early, preventing catastrophic failure. Engine management transformed from reaction to prevention. Losses dropped. Confidence grew. The B-29 slowly transformed from a death trap into a machine crews believed they could survive. But deep inside the factories, another revolution was taking place. The R-3350 was also suffering from inconsistent manufacturing quality. Parts that were technically within tolerance behaved very differently under extreme stress. Engineers realized that traditional tolerances were meaningless at these temperatures and loads. Manufacturing had to change. Statistical process control was introduced across the production line. Instead of accepting a range, factories aimed for a target. Variation was no longer tolerated. It was hunted down and eliminated. Tooling was redesigned. Heat treatment processes were refined. Assembly sequences were rewritten from scratch. Like the Packard Merlin before it, the R-3350 evolved from a hand-fitted nightmare into a controlled system. By late 1944, the difference was undeniable. Engine fires dropped sharply. Mission aborts decreased. B-29s began flying longer missions with confidence. The bomber that had nearly failed was now ready to deliver on its promise. And then came the moment that proved everything. March 9, 1945. Hundreds of B-29s lifted off from bases in the Mariana Islands. They flew lower than before, slower than doctrine demanded, carrying incendiary bombs designed for Japan's wooden cities. The engines held. Formation after formation reached Tokyo. What followed reshaped the war. Firestorms consumed the city. Japan's industrial capacity collapsed. The B-29 became the weapon it was always meant to be. Not because it was perfect from the start, but because engineers refused to surrender to its flaws. After the war, the lessons of the B-29 engine crisis changed aviation forever. Cooling science advanced by decades. Engine monitoring became standard. Reliability replaced raw power as the true measure of performance. Failures were no longer hidden or ignored. They were studied, dissected, and transformed into doctrine. Modern jet engines, with their thousands of sensors and incredible reliability, trace their philosophy directly back to the painful lessons learned inside the R-3350. Like the Packard Merlin, the Superfortress proved that engineering progress is not clean or linear. It is forged in failure, pressure, and relentless problem solving. Today, restored B-29s still fly. When their engines thunder across the sky, you are hearing more than noise. You are hearing the sound of engineers fighting physics and winning. You are hearing the echo of factory floors filled with stress, exhaustion, and determination. History remembers the battles. It forgets the nights spent staring at broken parts, refusing to believe the problem was unsolvable. But those nights mattered. Because wars are not won when weapons are invented. They are won when someone figures out how to make them work, every single time, under the worst conditions imaginable. The story of the B-29 Superfortress is not really about an airplane. It is about a way of thinking. It is about the moment when engineers realized that raw power alone was no longer enough. Bigger engines, more fuel, and thicker metal could not solve every problem. Control mattered more than strength. Understanding mattered more than speed. The engineers who saved the B-29 learned that when a machine becomes extremely complex, even small mistakes grow into deadly failures. A tiny oil leak could destroy an entire aircraft. A small airflow error could kill a crew. This forced a new philosophy. Every system had to be predictable. Every part had to behave exactly as expected, not most of the time, but all the time. manufacturing was no longer just about building parts. It became about managing variation, eliminating uncertainty, and respecting physics instead of fighting it. These engineers were not famous men. They did not give speeches or lead armies. But their decisions saved thousands of lives and made long-range strategic bombing possible. Their work proved that engineering is not just mathematics and metal. It is responsibility. Because when an aircraft fails at 30,000 feet, there are no second chances. When historians talk about World War II, they focus on battles, generals, and weapons. But the real victories often happened far away from the front lines. They happened in factories filled with noise, heat, and pressure. They happened in test cells where engines screamed until something broke. The Wright R-3350 and the Packard Merlin share the same lesson. Brilliant ideas are useless if they cannot be built reliably and in large numbers. British engineers gave the world the Merlin's revolutionary design. American engineers learned how to produce it perfectly, again and again. The same story repeated with the B-29. Designing the bomber was only the beginning. Making it survive mission after mission was the true victory. These engineers fought a different kind of war. A war against heat, vibration, tolerance, and time. They lost battles. Engines failed. Aircraft crashed. But they learned from every failure. And that learning turned disaster into dominance. This is why engineering quietly shapes history. Not through glory, but through persistence. So the next time you see a B-29 Superfortress at an air show, stop and listen carefully. That deep, rolling thunder from its engines is not just noise. It is the sound of thousands of problems solved one by one. It is the sound of engineers refusing to accept that something was impossible. It is the sound of failure turned into reliability, and chaos turned into control. Those engines carry the memory of nights spent in factories, of test pilots who trusted machines that were still learning how to survive, and of engineers who knew that if they failed, history would change for the worse. The B-29 helped end the war, not because it was perfect, but because it was improved relentlessly until it worked. And that is the true lesson of this story. Wars are not only won by courage in the cockpit or strategy on the map. They are won by people who solve problems when no one else knows how. If you want more stories like this, stories about the hidden engineering battles that shaped the world, subscribe to this channel. Because these are the stories they don't teach in history class. And without them, history would look very different.